When I learned about PCA, I heard things like eigenvalues of a correlation matrix or singular value decomposition, but it took me quite a while to understand how these things are connected because singular values are usually hidden deep in linear algebra books, and the explanations on the internet aren't too helpful. But I think one line of reasoning can give a good understanding of these topics. Let's take a look at the correlation matrix first. Let A be a matrix with a standardized column Ci, and we can denote the correlation matrix as A transpose A, which means we will have the correlation or dot product between the first column and all other columns on the first row, between the second column and all other columns in the second row, and so on. We will denote it as C for later. Note here that symmetric n times n matrices will have n eigenvalues. Let's continue with the reasoning how things are connected. Let V be a vector that gets scaled by lambda after applying A, which looks like the definition of eigenvalues, but in our case A isn't restricted to be a square matrix. Now let's take the standard dot product of our vector with itself. Since the dot product is bilinear, we can pull the lambdas together, and on the other side we can get rid of the brackets, and we reach an expression which looks familiar because A transpose A is our correlation matrix. And since our correlation matrix is just a symmetric matrix which acts like a scalar, we can give it a scalar name. And we reach an expression which looks like the definition of eigenvalues again. So sigma is the eigenvalue of our correlation matrix C. And it acts the same as lambda squared. And if we take the square root of this expression, we get something that is called the singular value of A. So to sum it all up, the singular value of A is the square root of the eigenvalue of our correlation matrix A transpose A. And that's it. Hooray!